Welcome back to the deep dive. Today we're cracking open a really big one. Stratospheric Aerosol Injection, SAI.
Yeah, it's that proposal you always hear about for, like, rapidly cooling the planet if things get desperate.
Exactly. The emergency brake idea. Mimicking big volcanic eruptions, pumping sulfate aerosols way up high. You always hear those three words. Fast, cheap, and imperfect.
And that's precisely why we need to dig deeper today. Because, almost all the modeling, the research, it focuses on the best case scenario. Perfect deployment, perfect conditions.
Which isn't reality.
Not even close. Once you factor in the messy stuff, the actual physics of the particles, the geopolitics, the economics, these real-world limits basically squeeze the possibility of a truly low-risk SAI strategy down to almost nothing.
Right. So that's our mission today, to really unpack how these practical hurdles mess with the plan, especially when we try to use maybe safer materials than sulfates.
Yeah, and just to set the scene on cost, the number floating around is something like, what, $10 billion a year?
Per degree Celsius of cooling, yeah, that's the theoretical starting point.
Keyword, starting point. We're about to show you why the real cost and the real risk could be way, way higher. Okay, let's start with maybe the biggest hurdle, governance. Or, the lack of it, potentially.
How countries might coordinate or not coordinate.
Exactly. Because the level of global agreement, or lack thereof, fundamentally dictates how much control you actually have. Control over where you inject, how high, what time of year, how much material.
And why is that control so vital? What happens if, say, one country just goes rogue and starts spraying?
Well, the big danger is unevenness. You end up with a patchy cloud of aerosols up there, what we call the stratospheric aerosol optical density, or the SAOD. If that cloud isn't spread smoothly around the globe.
Oh.
Yeah, right. You risk serious knock-on effects down here where we live in the troposphere. The main worry is shifting the ITCZ, the Intertropical Convergence Zone.
That huge band of rainfall near the equator.
The very same.
Yeah.
If you push that north or south, you are fundamentally changing rainfall patterns for billions of people. Massive droughts in some places, floods in others. It's incredibly risky.
And you mentioned another atmospheric effect, locking the QBO. What's that?
The quasi-biennial oscillation. Think of it like a major wind pattern high up in the stratosphere that flips direction every couple of years or so. It helps regulate weather patterns globally.
And locking it would
Mess things up significantly.
Yeah.
It could disrupt weather predictability, maybe even impact ozone layer recovery. So yeah, getting that aerosol cloud smooth and uniform, it's everything.
Okay, so the ideal scenario is this perfectly centralized one. Everyone agrees, works together.
Right. Synchronized global governance. And you can be smart about it. Use what we know about how air moves in the stratosphere, the Brewer-Dobson circulation, to inject in multiple places, mid-latitudes, both hemispheres.
To get the most even spread possible. That's the low-risk path.
That's the theory. But then there's the other path, the decentralized scenario. If you can't get agreement, maybe smaller groups, even non-state actors, just start injecting locally.
Which leads straight back to that uneven, asymmetric SAOD problem.
Exactly. And not only does that increase the risk of those regional climate shifts we talked about, but the aerosols themselves don't work as well. They have shorter lifetimes up there. They don't reflect sunlight as efficiently.
Meaning you have to pump more stuff up there to get the same cooling.
Precisely. Which just cranks up all the associated risks even further.
Okay, but let's imagine for a second we achieve that perfect global harmony. We still have physical choices to make, right? Like altitude. Does higher mean better?
It's a trade-off. Injecting higher, say above 20 kilometers, generally means the aerosols hang around longer and have a stronger cooling effect per particle. That sounds good.
But there's always a but.
But yeah, it also seems to be worse for the ozone layer. High-altitude injections give more opportunity for ozone-destroying chemistry to happen. One study we looked at showed nearly double the ozone loss in the Arctic Spring at high altitudes compared to lower ones.
Wow, 18% ozone loss versus 8%. That's significant. Does that mean high altitude is just too risky?
It might push the optimal altitude down, depending on what you're injecting and how much. For sulfur, at least, some models suggest a kind of sweet spot between maybe 17 and 19 kilometers, balancing the cooling effect with the ozone risk.
And timing matters too, you said. Winter versus spring injections.
Yeah. Injecting in winter means the stronger stratospheric circulation sprints things out well, potentially giving longer residence times.
Okay.
But injecting in spring might be better overall. You time the peak aerosol concentration to match when the sunlight is strongest in the summer. That could be better for specific goals, like helping Arctic sea ice recover, and might also slightly reduce the ozone impact.
Right. It's complex. Okay, so even with perfect coordination, Choosing the right altitude, the right season. It sounds like we're still bumping up against fundamental problems with the stuff we're actually injecting.
Exactly. Which brings us to the material itself.
Mm.
So sulfate specifically injecting sulfur dioxide, SO2, which turns into sulfate aerosols. That's the default starting point. It's what volcanoes do.
But we know they have issues. You mentioned ozone depletion.
Right. And they also absorb some infrared radiation, which actually warms the stratosphere itself. That has its own set of potential knock-on effects.
So that's why researchers are looking for alternatives, solid particles.
Precisely. Things like minerals, calcium carbonate, which is basically chalk or limestone dust,
Okay.
alpha lumina, titania, zirconia, even, theoretically, tiny industrial diamond particles. The hope is they might scatter sunlight better and have fewer unwanted chemical side effects, less ozone damage, less stratospheric warming.
Sounds promising. But can we actually get enough of this stuff? This is where the economics come in, right?
Oh, absolutely. It hits a major snag. These grand SAI strategies assume you can just, order up millions of tons of ultra-pure nanoparticles.
Yeah.
But if you suddenly need, say, 5 or 10 times the current global production of something,
The market might not cope.
especially for materials where demand is pretty fixed, what economists call inelastic. Our sources point out that for things like calcium carbonate or alumina, even though there's a lot produced globally, a sudden massive demand spike from SAI could seriously strain the market and send prices haywire.
Because current users still need their supply.
Right. It's not like people will just stop using cement or aluminum if SAI needs the raw materials.
And what about those more exotic options? You mentioned diamond.
Yeah, diamond is kind of the extreme case. It might have great optical properties, but the amount needed for a global SAI program would just dwarf the entire current world production of industrial diamonds.
Like by how much?
We're talking potentially way over 100% of the current market. It's a logistical impossibility based on supply alone. Forget the cost for a second. You just can't get it.
Okay, so diamond's out. What about zirconia or titania? The sources said their markets were a bit more elastic.
A bit more responsive to price changes, yes. Their price elasticity of demand is less severe, meaning production might ramp up more easily if the price goes up. But you're still talking about huge quantities.
So let's assume we want to avoid sulfates. Diamonds are impossible, and we pick something abundant like calcium carbonate or alumina. We solve the supply issue, maybe. Now we actually have to get these fine powders up there and spread them out.
Now you've hit the real engineering nightmare. This is maybe the most underestimated problem for solid aerosols, getting them dispersed properly.
What do you mean? You just spray them out of the plane?
If only it were that simple. See, for these solid particles to work efficiently, reflecting sunlight, they need to be tiny individual particles, monomers we call them, submicron sized.
Okay.
But these kinds of fine powders are notoriously difficult to handle. They're classified as Geldart Group C materials.
Geldart Group C sounds technical. What does it mean in plain English?
Think about trying to pour really fine flour or talcum powder through a small nozzle. What happens?
It clumps up, clogs the nozzle.
Exactly. These nanoparticles have strong forces pulling them together, cohesive forces. So instead of dispersing as individual particles, they stick together in big clumps or agglomerates. They are fundamentally hard to fluidize.
So they won't spread out into that fine haze we need.
Right. And the scale difference here is just massive. Lab experiments on dispersing these things, they might be working with flows of maybe a couple of kilograms per hour.
Okay.
But for actual SAI, you need systems capable of injecting over 5,000 kilograms per hour per aircraft, probably.
Whoa, that's a huge leap. How do you even declump them at that scale?
It requires serious engineering. Multiple steps, using high-speed impacts, maybe Venturi vacuums, basically blasting them apart forcefully right at the point of injection.
Yeah.
It's energy intensive.
And does it even work effectively up there in the thin stratospheric air?
That's another critical problem identified in the research. The physics of breaking these clumps apart depends on aerodynamic drag forces ripping them apart versus the cohesive forces holding them together. Engineers use something called the Weber number to figure this out. Okay. And the simulations show that if you just try to use the surrounding high-altitude air, which is low pressure, but moving fast relative to the aircraft, the drag force is surprisingly weak. Too weak to effectively break up those stubborn agglomerates.
So just spraying them into the thin air doesn't work. What does work?
To get enough force, you actually need high-pressure, relatively slow-moving gas blasting through the particle.
High pressure at high altitude. Where does that come from? You'd have to bring it with you.
Pretty much. You either need incredibly heavy, powerful onboard air compressors, Or you have to carry tanks of a highly pressurized carrier gas along with the aerosol payload.
Wait a minute, carrier gas, how much are we talking about?
The modeling suggests that to get sufficient deagglomeration, the mass ratio could be something like 35 to 1.
35 to 1. You mean for every 1 kilogram of aerosol powder you want to inject?
You might need to carry and use about 35 kilograms of pressurized gas just to disperse it properly.
That's insane. That completely changes the payload calculation.
It's a potential showstopper, logistically and economically. Most of the cost of SAI deployment is the aircraft buying them, flying them, maintaining them. If 97% of your payload mass per flight is carrier gas and not the actual cooling agent.
Your cost per kilogram of actual aerosol delivered skyrockets?
Exactly. That $10 billion per year figure we started with, this dispersal challenge alone could potentially push the real cost up by an order of magnitude, maybe more.
10 times the cost. So $100 billion a year? Maybe. Just because the powder is sticky?
Potentially, yes. And think about the alternative. What if, because it's so hard and expensive, operators just don't bother with proper dispersal? They just inject the clumpy powder.
What happens then? Do the clumps still work?
They totally lose their advantage. The whole point of using solids was their potentially better scattering efficiency compared to sulfates. An individual monomer might scatter sunlight, say, 3 times better than a sulfate particle. But if you inject them as clumps, especially messy fractal clumps, they scatter much less light, and they fall out of the stratosphere much faster. Their cooling efficiency just plummets.
So you'd have to inject vastly more clump material to get even a small cooling effect.
Which brings back all the risks, maybe even amplified risks, including ozone loss that you were trying to avoid by not using sulfates in the first place. It becomes self-defeating. #tag conclusion and final takeaways. So when you put it all together, what this deep dive really shows is how these practical constraints just pile up.
Yeah, it's like a 3-pronged attack on the idealized models.
Exactly. You've got the governance problem. Failure there leads to risky, uneven deployment. You've got the supply chain problem. The best materials might be unavailable or disrupt markets. And then you have this massive engineering challenge, actually getting solid aerosols dispersed effectively.
Each one pushes real-world SAI further away from that neat, low-risk concept we see in simulations.
And the trade-off becomes incredibly stark, especially with the solids. To make them work well enough to be potentially safer than sulfates, you face this huge engineering hurdle that could multiply the cost massively.
A 10-fold cost increase, maybe? That's a huge price tag to pay for potentially marginal risk reduction.
Which is why, realistically right now, sulfates are still seen as the more logistically feasible option, despite their known risks. The engineering is, relatively speaking, simpler, and the risks are better understood, even if they're significant. They don't have that massive cost uncertainty tied to dispersal.
So developing a genuinely low-risk SAI strategy using these better solid materials, it depends entirely on solving these really fundamental engineering and logistical problems first.
Absolutely, those gaps are enormous.
You know, so much of the public debate around SAI focuses on, well, what happens if it works? The unintended consequences, the moral hazards.
Right, the termination shock, regional climate changes.
But what this shows is that even the most promising materials, the solids designed to be safer, might be practically impossible to deploy optimally due to these engineering and cost barriers.
Yeah.
So here's the final thought for you to chew on. If the best, safest version of SAI requires incredibly strong global coordination to avoid dangerous side effects, and the array requires overcoming maybe a 10-fold cost increase because of these dispersal engineering nightmares, what happens in the real world? Doesn't that difficulty, that sheer cost, inevitably push anyone contemplating this, whether it's the nation or someone else, towards the easier, cheaper, but ultimately much riskier and less effective options, like poorly dispersed solids or just sticking with sulfates or doing it unilaterally?
It certainly creates that pressure. The path of least resistance leads towards higher risk.
So maybe the biggest risk of any SAI strategy isn't just the technology itself, but how the unavoidable real-world difficulties interact with our inability to govern it perfectly. That combination seems almost designed to lead us down the riskiest path.
A sobering thought indeed.